Hi, just one other theorem from section 2.2, and then I thought I would do a few examples because they're not so bad yet. But again, 2.3, 2.4 will pick up a bit. There is an important theorem in this section that I think often gets overlooked, and I do have a homework problem that pertains to this theorem, and I know a lot of people don't realize that this theorem is being used in a problem. Sometimes it's hard to pick out, but this is when you're trying to find a set that has elements, how many subsets it has. So a set with n elements has 2 to the n subsets. So for example, imagine that you're making a pizza and you have 3 ingredients you could use: green peppers, onions, and tomatoes. How many unique pizzas could you make if you used none, 1, 2, or 3 of them? So how many subsets of this set of 3 elements are there? So for example, on your pizza you could have none of these items on there, or you could have exactly 1 item. So you could have green pepper, you could have onion, you could have tomato, or you could have any 2 items, so like green pepper and onion, or green pepper and tomato, or onion and tomato. So there's another. So 1, 2, 3, 4, 5, 6, 7. The last one is all items. So there's 8. So 2 to the third is 8. So there's 8 different possible pizzas you could have that include none or all of these ingredients. None or up to all the ingredients. A lot of times when you're trying to figure out, like even in the last section of what I was doing, when you're trying to figure out a counting situation, how many elements are possible, a lot of times it's nice to use a tree diagram. And I was kind of doing that previously. I don't think maybe I'll start this out. Bill and John keep playing chess until one of them wins 2 games in a row or 3 games altogether. What percent of all possible cases does the game end because Bill wins 3 games without winning 2 in a row? So we'll just start a tree. I probably won't do the whole problem, but in the first game, what could happen is Bill could win or John could win. Okay, and we're not done because somebody had to win 2 in a row or 3 games total. So the next set of games, Bill could win or John could win, and down here, Bill could win or John could win. If we're going this route, Bill has won 2 in a row, and this branch of the tree is done, and same here, this branch of the tree is done. If they continue, let's say, the situation Bill and John or John and Bill, then we could have another game. So this would be Bill and John. And in this case, or 3 games altogether until one of them wins 2 games in a row or 3 games altogether. So this branch is still going. John has won 2 in a row, so we stop. Same deal here. Bill or John. Bill has won 2 in a row, so we stop. This branch keeps going, but it's not going to go much further. And then again, the end, I'm just looking at what percent of all the cases has a game ending with Bill winning 3 games. But the way I'm doing this is building a tree. I think it would be a little bit tough to do it, just without kind of mapping out the situation. So these are just some practice problems. Number 1, that's pretty nice. These are a couple license plate ones. How many different 7-place license plates? So 1, 2, 3, 4, 5, 6, 7 places are possible if the first 3 places are occupied by letters and the final by digits. Letters and digits may be repeated. So there's 26 letters that are possible. 26 times 26, and it's 26 because I can have repeats. The final 4 digits are 0 through 9, so there's 10 choices times 10 choices times 10 choices. So again, I'm happy with this, or you could just say 26 to the third times 10 to the fourth. I don't expect you to multiply that. 3 is going to be similar. 4 is also not bad. You have a fraternity that has 30 members, and they're trying to elect a president, vice president, and treasurer from the fraternity, what's the total number of possible pres, vice pres, treasurer tickets? You can't have one person be all three. So if this is the president, vice president, treasurer, there's 30 choices for the president, 29 choices because you can't repeat for the vice president, and then 28 for the treasurer. And again, you can leave it like that. I'm happy. This is another just initials counting. Let's see, example 6. And I have all these on the solutions, the lecture with solutions if you want to see copies of all of them. A multiple choice exam has 15 questions, each having 4 possible answers, of which only one is correct. If the questions are answered at random, what is the probability of getting them all correct? So the probability of getting the first question correct is 1 out of 4. And now it's just probably a question, do you add or multiply? But I want to get the first question correct and the second question correct, so that's a 4th for the second and a 4th for the third. And so I'm multiplying. I want this and this and this and 1/4. So this will come out to be 1/4 to the 15th. 7 is tough if you've never really thought about doing this as a tree. I had to do it a while that way before I really felt good about it. But to figure out how many divisors a number has, first you want to break it down into its, I should know the name of this, right? I break it down as far as you can into its prime factorization. And then you could think about it, the way to build, or anything that divides this is of the form 3 to the 0, 3 to the 1, and 3 to the 2. These all divide 5, 5, 1, 2, 5. Now it could be any combination with the 5. So this could be 5 to the 0, 5 to the 1, and 5 squared, also and 5 cubed. So this is 1 divides that, 5 divides it, 25 divides it. Same way I'm going to branch off, 0, 1, 2, 3, 0, 1, 2, 3. And then the 7 raised to the second power. So you can kind of see the number of divisors I'm going to have. I'm going to get 3 possibilities from the 3 times 4 possibilities from the 5s times 3. So it actually is going to have 36 divisors. I hope that one makes sense. That's, like I said, you could start with a smaller example, and that's how I kind of figured out that pattern, what was happening in the tree helped me too. I'll just include 8, and then yeah, here's another bonus. I think the story, I took it from the book. It's kind of funny the way they wrote it, and it's a little bit confusing. So you can ask me if you want to check this one. Again, it's a little bit tedious, and I don't know that there's a nice pattern to figuring out the answer to this one. I actually had to map it out. I don't think there's a nice way to say, oh, I'm just going to figure out this one branch and then multiply by 4 or something. It doesn't work that way. So if you want that one, this one's due on Monday. And here, I might as well add this last one. There are N types of a drug sold to reduce acid indigestion. N drugs is taken, I'm going to take a random sample from this big capital N. So there's capital N of them in. And I'm going to take a random sample of N of them out. And I'm taking them with replacement, which is kind of weird. Because if you take one you don't like, are you really going to put it back on the shelf? But that's the way the problem's worded. So what's the probability that brand A is included? So probability that you pick a sample of N and brand A is included. Well, it could be included as the first one, the second one, the nth one. So again, the easiest way to go backwards, 1 minus probability brand A not included. And the way it's not included is you pick, out of the N drugs you picked, every time you picked one, you didn't pick brand A. So the probability of not picking brand A, N minus 1 over capital N of them. These capital N minus 1 are not brand A, because one of them is brand A out of the capital N. So this is the probability of not choosing brand A. and not choosing it and not choosing it and not choosing it raised to the little n power, because every time you pick one, you put it back into the population again. So it's like if there were 4 drugs in here, let's say this is brand A, B, C, D. The probability of not picking A would be 3/4, and then not picking A again would be 3/4, and not picking A again would be 3/4. So I think you can see kind of how a lot of times if I can't get something with the random capital N's and N's, I'll make a smaller example and think about how to work that, and usually I can figure it out if I just start with a smaller example. So I hope those were helpful, and then next week we start permutations, combinations, so make sure you feel comfortable with the basic counting because we'll get more difficult and build on this next week. Okay, so I hope you have a nice weekend.